Now it is time to conclude our discussion of public key cryptography and actually conclude this course. So, final topic that we are going to talk about certificates and why we are using them. And then we will maybe briefly mention what is the current status of public key cryptography and how quantum computers can affect this area. So let's talk about certificates. The problem with the public keys is that it's distribution. So even if everybody can generate their own public and private keys, we need a way to distribute our public keys. So it is a problem. One way of doing it is public announcement. So you can attach your public key to the end of your emails. For instance, some people who use PGP does this. If you have a web page, you can put it there and say that this is your public key. Anybody wants to communicate with you can use that public key and so on. But of course, this has some problems because one problem is that you cannot search the internet all the time to find the public key of everybody. And second of all, people might impersonate you. If you don't have a web page, somebody can create a web page about you claiming that they are you, and they can put a public key there and impersonate you. So public announcement actually is not a good idea. Another idea is to have a publicly available directory like the phone books we had years ago. But the problem with the phone books applies here, because if you remember years ago, when you find somebody's phone number from the phone book, when you call them, it turns out that they moved to a different place and you're actually talking to the people who moved to that apartment. So same thing will apply here. The directory would be out of date and it should be updated constantly, and constantly updating the public key of everybody is not something easy. And again, people might impersonate you and so on. So a better solution is to have a public key authority, somebody that keeps everybody else's public keys, and whenever you want to communicate with them, you can go to this public key authority and ask for the public key. For instance, think about it, we use this idea, assume that we are using this idea for web pages. So whenever you visit a web page, and if it is an encrypted communication like SSL TLS, in other words, if you visit the web page as not HTTP but HTTPS, then you need to know their public key and so on. So you can go to public key authority all the time to learn the public key of this web page or anybody you want to communicate. But as you can imagine, storing all of the public keys at a single authority would cause a problem. It's a single point of failure, and also constant demand would cause a denial of service attack. So it is not easy to respond everybody in a timely manner. So this is why actually we have public key certificates. So let's see how a public key certificate is used. So it is something like this actually. So in this example, it is referred to as Bob's certificate. So Bob has some ID information. Bob has public key, and there is a certification authority, and its information also is kept in this certificate. Then this information is put inside a hash function like SHA-2 or SHA-3. Then the hash of this certificate is signed with the private key of the certificate authority, and the result is added at the end. So this whole thing is your signed certificate. So whenever somebody receives this certificate, what they do is take the hash of the public information here, they obtain this hash, and they also decrypt this signed part with the public key of the certificate authority and obtain something here, and they check if these two things matches. If they don't, then the signature is wrong or certificate is not correct. But if it is the same, this means that this certificate authority really sign this information. So this way you kind of have the Bob's public key from the certificate. So it is all you need to is to store the public keys of certificate authority, so that you don't need to store a lot of information. So you don't need to contact with anybody to check the correctness of a certificate. So this is actually what browsers does. They have public keys of almost every certificate authority, and when you visit a web page and so on, when they need to check the certificate, this is what they do. Of course, the default setting of a browser is to accept the signed certificate from every certificate authority. But if you don't trust some of the certificate authorities, you have to go to settings and deselect those certificate authorities, which people most of the time doesn't know this. And there are some standards for certificates. For instance, the most used one is X.509 Certificate. So there are some versions of it. So initial version was this. In the second version, they had added a little bit more headers, let's say, and so on. So it stores the certificate, stores the version, certificate serial number, algorithm and parameters. These actually defines which signature algorithm that is going to be used and so on. Issuer name, period of validity, and all of the certificates has a expire date, subject name, and subject's public key info, like the algorithms, whether you are using RSA or elliptic curve and so on, parameters and key, public key, and so on. And this actually signature contains the signed part of this information. So of course, once you create a certificate and put a expire date, all of the people who check the certificate will think that that certificate is valid under the expiration date. But sometimes a certificate might be revoked by certificate authority. In that case, they have a certificate revocation list, and browsers and people who use this certificate should check if the certificate is revoked or not. So let's conclude with key lengths. This picture actually taken from the keylength.com. You can check that web page for up-to-date information. So NIST recommendation for key lengths is currently as follows. They say that 80-bit security is no longer enough. It can be only used in the legacy cases. But since 2016 to 2030, they say that 112-bit security is enough. And triple DES actually provide this kind of security. And if you are okay with this much security, then when you use RSA, your factoring modulus n should be has a size of 2048 bits. In other words, the value n we talk about should be at least this big. And for the discrete key logarithm, the key can be twice of 112, which is 224, and the group modulus should be at least 2048 bit, and elliptic curve, the key can be just twice of this value. As you can see, we don't have a sub-exponential algorithm to break elliptic curve discrete logarithm problem. This is why we only multiply it with 2. This comes from Pollar's row algorithm actually. But for RSA, the factoring modulus should be larger because we have sub-exponential time algorithms. We said that here triple DES is okay, but as far as I know recently, NIST, even though they said that 112-bit security is okay, they removed triple DES from their recommended list of algorithms. So currently they only suggest use of AES. And NIST also says that probably until 2030 and beyond, 128-bit security would be enough. So you can use AES 128. Your RSA key should be, factoring module should be at least 3072 bits. And as you can see, these are just twice the multiple of the security you require due to the, again, Pollar's row algorithm. But if you require military-grade security, NIST suggests 256 bits security. You can use AES 256, but now your RSA modulus should be more than 15,000 bits. So as you might imagine, this would be really slow in software, and it would be very costly to implement on a hardware. So this is why most of the time for higher key lengths, people prefer elliptic curve cryptography. And in Bitcoin, in most blockchain technologies, they use elliptic curve cryptography. And if you, of course, increase the size of your security in bits, due to birthday paradox, the hash function that you are going to use should have at least twice the size of these bits. So for 256-bit security, you can use SHA-2 with 512 bits, or you can use SHA-3 again with 512 bits. So what happens if somebody invents a general purpose quantum computer? So we have an algorithm that can break this hard problems that we talked so far, like integer factorization, discrete logarithm, and elliptic curve discrete logarithm problems. They can be solved in polynomial time on a quantum computer, but nobody hasn't invented such a computer yet. Also, quantum computers reduce the security of symmetric key cryptography to half. So it is enough to double the key size. For example, moving from AES-128 to AES-256 would be enough to have security for symmetric key cryptography. But as you can see, if you lose confidence in these problems, then all of the current algorithms we use, like RSA, Al-Gamal, diffie-hellman key exchange, elliptic curve cryptography, goes to waste, and this would prevent e-banking or e-commerce, and so on. So for this reason, we need quantum safe algorithms for public cryptography in case somebody builds such a computer. So there are some, currently competition is going on, which is called post-quantum key cryptography competition, organized by NIST. So there are some algorithms are competing there, and some of the algorithms there use elliptic curve cryptography again. So we don't need to throw all of our knowledge in these areas, but their security depends on different problems like finding isogenies and so on. So a few years ago, NSA published a note saying that so far, NSA always supported elliptic curve cryptography and suggested migration from RSA to elliptic curve cryptography in the future. But in 2015, NSA suggested not to waste time migrating from elliptic curve cryptography to RSA, but suggested development, standardization, and commercialization of new quantum safe algorithms. And as I mentioned, ECC and RSA are not quantum safe. This announcement puzzled many people, and as if somebody is getting close to building a quantum computer, and since 2015, actually nobody announced such a thing. And however, considering the budget of NSA and how much they reserve for post-quantum cryptography, it is highly unlikely that they are about to build a quantum computer. So my personal opinion for this recent policy of NSA is that probably they lost since the bug in actually the backdoor in dual elliptic curve deterministic random bit generator is discovered. NSA wanted people to stick to RSA instead of ECC because at least there are some algorithms that can break RSA faster than elliptic curve cryptography. So if you want more information about this thing, I recommend you to read A Riddle Wrapped in an Enigma by Neil Koplis and Alfred Menezes, and you can download the PDF from here. So this concludes our discussion of public key cryptography, and actually this also concludes our course, CSEC 507, titled Applied Cryptology. So thank you for listening.